I'm James Diuri. I'll be talking about water sanitation in small farms. That doesn't mean if anybody is here and has a large farm, a big farm, the principles should be the same on small farms as well as on big farms, but we want to address the smaller farms because they don't like to invest so much money as the big farms do. So I'll try to address the requirements of water sanitation on only small farms. So water is important in farms, both for irrigation and for washing produce. And it is a vital component in our lives. If you think about water, it covers 75% of the earth. And in our bodies, you have about the same percentage of water. So water is important everywhere. Water is also a medium in which many animals as well as inanimate components are to be found. And so when we wash our produce or drink water, we want to have it clean, and even better, we want to have it pure. And as we address small farms here, like I said, the principles, some of the principles that we talk about here will be applicable to large-scale farms as well. And so why should we be concerned about safety or sanitation of water? If I just give a little bit of a story here, in the year 2000, there was a foodborne illness that was experienced in Canada, and it was traced to a well that was contaminated with farm sewage and which had been used to irrigate spinach. So water is important. Closer to home and closer to this period in time, in 2010, you are all familiar with the story of cantaloupes that came from Colorado and that were eaten all over the United States and got over 300 people sick and 15 people or maybe 16 people dead. And this was traced or has been alluded to the fact that the farm ran out of a sanitizer and used water that had not been sanitized. The full report is yet to be made, but these two examples underline the importance of sanitizing water. What you see in those two pictures are bacterial cells, both of E. coli and Salmonella, and I want to draw your attention to the E. coli that is mentioned here, the E. coli 0157H7. It is so designated because there are very many different types of Salmonella as well as E. coli. But let me talk about E. coli here. We have so much of E. coli ourselves in our bodies, but our bodies have learned how to cope with this E. coli. But when you have a mutant like E. coli 0157H7, which the body cannot cope with, then you get all sorts of things like nausea, diarrhea, dysentery, and could result to death. We would all like to use municipal water for all our washing and drinking and that kind of those kinds of needs. But you will agree with me that municipal water is expensive and inadequate during the heat of the summer when we need water most to clean up these food commodities. There is a shortage of supply. You can't even water your gardens, your lawns. Surface water, on the other hand, the ponds and the lakes and the rivers or the creeks, is in plenty. But that's the most exposed water. That's the water with the highest risk, and we are going to see in a moment why. The old adage, or the old saying that prevention is better than cure, is what we advocate in extension when we address water safety issues. We also address the demands by the Food Safety Modernization Act, which is a new law that was signed recently to check that contamination of food is minimized as possible, as low as possible, so that we don't have any foodborne illnesses. We also, in extension, offer what we call good agricultural practices workshop, and this is a set of conditions and growing practices and harvesting practices, processing practices, handling practices, how workers should be hygienic, how water should be sanitized. All those things are offered in good agricultural practices. And water is one of the areas that we address in this class. So we talked about water being contaminated. Where does contamination come from? The two major sources of infection in water, or infestation in water, are humans and animals, particularly fecal matter. We introduce a whole lot of E-Coli, especially in drinking water, through people that have diarrhea, or from cows that are upstream from where we are. The droppings from cows usually contain quite a load of E-Coli, and therefore proper composting is recommended under the manure management point that you see there, and harvesting and that kind of thing is recommended not to be done so soon, especially if you apply raw manure into produce. All right, I'm talking to you from Will County, which is just about 60 miles south of Chicago. I also work in a county called Kankakee, which is just about 60 miles south of Chicago. So if I mention Kankakee a few times, you know why I'm doing that. It's because I'm here, and the public health officials that I talk to tell me a few of the things that I'm going to share with you. So different water supplies are recognized in Kankakee. As you can see there, the community, the non-community that's non-transient, the non-community that is transient, semi-private wells, those that are shared like in a village, and then private wells. And for purposes of today's presentation, it is the private well that is of most concern, because that's where most small farms get their water from. And how can we be sure that the water we use is adequately safe or adequately well sanitized? To begin with, you want to know what you are starting with. So every time you start the year, or every time you suspect you need to test your water, or you own a new farm, you want to know what kind of water you're starting off with. Now in Kankakee, the public health officials tell me that they do water sampling regularly for, well, at least for new wells. What was in that area where the new well was dug? And if I refer to Kankakee, some areas, there was one time a gasoline pipe burst. So we expect those days when leaded fuel was being used, probably because of that bursting, there's lead in the soil, in the underground. So if somebody was to do a well there, they would want to check. And then during repair of wells, who knows what was introduced by the workers, or some pieces of rusted metal fell into the well, or whatever. So they want to check that. And then they do routine well sanitary surveys, especially upon request, and also because in non-community water supplies, schools and medical institutions like hospitals may be involved. And therefore, water must be tested in all those situations. Now, if in any situation you have a well and you think that the surface water has flowed into the well, who knows what was in that surface water? During floods, as in like the recent storms in Manhattan Island, Sunday, who knows what happened to, say, outhouses? They could have filled up with water, and that water could have flown into wells. Or when you have excessive rain, the holdings where you have cattle upstream, that flowing water could carry cow dung with it, and that would carry lots of E. coli, for instance, into downstream areas. And everybody should be able to access their public health offices to ask questions about the health of their water. And it's also necessary during our GUTS classes, we do tell people how they should collect water samples. And we are not the best people to be telling them how to do that, but we've been told by the public health office, and in this case in my county, how to collect a water sample. The best thing to do, and we recommend this, when you want your water tested, call the test lab or call the public health department, because they'll give you instructions. Besides, you cannot collect water in any bottle. They give you prescribed bottles that are, so to speak, sterile. They don't have any contamination in them, and they give you the best instructions. And so when you get home and you spout, you remove any filters or any aerators, because that area is a den. It's a place where you have so many bacteria residing. And therefore that spout has to be disinfected, because then the results wouldn't be a reflection of what your water is like in the well. So the sampling technique is important. Run your cold water for 4 to 5 minutes, wash your hands, and then work with both hands from that time on, because you use the one hand to uncap the bottle, the other hand is holding the bottle. Then you collect your water, do not touch the spout. Then you cap it after you've reached the level that is shown, and you don't touch the inside of lid or the bottle. And then Mondays or Tuesdays are the best times to be sampling, because you sample on a Friday and your sample will sit with the UPS, if it's UPS delivering, until Monday, and then the workers don't get to it until Tuesday. That's not the best time to be getting your water sample to these people. And the turnaround time could be a few days to a week if you do it right. So the health department here tests for the following traits. Bacteria is one of them, and nitrates are the other one. Those two they definitely do as a minimum. If they think that they have any reason to be concerned with lead or with arsenic, then they'll also do that. But if you have any reason yourself to be suspecting that lead could be a contaminant, they tell us to contact them first. So maybe that's the same thing everywhere else. So with bacteria, when they test and the results come, they want to have the results showing 0 bacteria in 100 ml. That means no bacteria at all. The number of bacteria, the E. coli, the coliform test, the E. coli that they find there is an indicator of the possibility of the amount of bacteria that you have in that water. Now, since it's possible to treat water and get 0, then they want that count as 0. One bacterium, just one cell of bacterium, can multiply into millions within a day or two, because its replication is geometric. 1 gives rise to 2, 2 gives rise to 4, 4 to 8, and it happens every 20 minutes. It divides. So that is very important that they check on that. Nitrates and nitrites. The nitrates will come from farms. It's on-farm deposition from on-farm by water that has just eroded the farm. That nitrate ought to be checked, because nitrates are very harmful to children under 6 months old. You probably have heard of what they call blue babies. When nitrates get into the blood of very young kids, then you get hemoglobin being inhibited from carrying oxygen around the body, and the babies look a bit blue. I guess that's what they look like. But it is harmful. Lead and arsenic, of course, are poisonous toxins that we don't want to get into our bodies. If you want to go, well, for those two tests, bacteria and nitrates, it's reasonably cheap, about $15 a sample, depending on where you take it. But if you want to have other tests like pesticides and volatile organic compounds and others, then you're going to have to pay a little bit more, and then you have to get very specialized laboratories. What would you do if your well was contaminated? We will talk about that in a second, and we'll talk about that in a slide to come. So it kind of a summary here. The various water sources we've talked about, or I probably mentioned, are municipal, private, or surface water. Private wells and surface water. In terms of risk, municipal water has the lowest risk. But even then, we recommend that you test it at least once a year, or at least when you start using it, because then you know if anybody asked you, if the EPA was to catch up with you, or FDA, or if you had a foodborne illness out of your place, you can use that to mitigate that. I only use municipal water. But we just said that municipal water is both expensive and sometimes inadequate. So private wells are the ones that we use most next, because first of all, the deeper wells don't have a very high infestation of bacteria. If you're doing 50, 60, 70 feet below the ground, then you don't probably have as much infestation in there of bacteria. However, we do have some very shallow wells, 5, 10 feet. I've seen that in my county. Besides, they are in very sandy soils, and you know that sandy soils will allow percolation of the nitrates we just talked about. So it's vital to have wells tested annually or as needed. So if you had a flood, if you had 6 inches of rainfall and there was too much rain and it got flooded, then it needs to be tested a few more times than just one. On the other hand, if it's not a very well-kept well, again, the risks are higher from pesticides are being applied near that well, needs to be tested a little bit more. Surface water, of course, like I said, have the highest risk. On the bottom right-hand picture there, if you're using that water and these cows are going in there, you know, besides drinking, you know what else they might do in there. So it may be highly infested with bacteria. So that needs to be tested quite a bit more. How do wells become contaminated? A variety of ways. I probably just mentioned them. When you have abandoned wells or not well kept, anything and everything could fall in there, from chemicals to small animals to soil that has contamination. This was a particular case of a donkey falling, so that's not contaminated. Well, I don't know if it is, but things could happen. You have corrosive pipes. This is a pipe that's taking electric wire down to the bottom of the well to where the pump is. Look at how corroded that is. Again, this needs to be checked every so often, and as I will recommend even at the end of this talk, the water components, the pipes, all those need to be checked regularly. I also hear of the words sanitation and disinfection being used sometimes interchangeably, and I attempted to define them. And if you see the second or third sentence there about sanitizing, I have said it is to remove unpleasant or undesired features, both by cleaning and sterilizing. So if you look at those two or three containers there, they don't look very clean. They ought to be washed with water, just water, before you now bring in water that has sanitizer in it. Disinfection, on the other hand, infers that you have living organisms. Infection is from a living organism. So therefore, you want to treat with a chemical or some kind of sanitizer that will destroy harmful microorganisms. Sometimes you don't want to use a chemical that is killing the harmful organisms first before you wash, because if you have that, it's going to absorb some of the sanitizers and will render them inactive, or you have to use more. Then I also want to use the word, I want to define the word oxidize. To oxidize, the simplest way to define this is to just chemically combine with oxygen. Wood, when you light up wood, oxygen is coming to it, and you may just consider that like a form of oxidation. On the other hand, when oxygen gets onto iron, like on your cars, you get iron oxide, and then you get what is rust. That's rust right there. That's an oxidation process. And some of the sanitizers we are going to look at or talk about today are actually oxidizers. The first 4, 5 of them here are chlorine, chlorine dioxide, ozone, and peroxyacetic acid, as well as hydrogen peroxide. They are all oxidizers. And when oxidation takes place, you get inactivation of sorts. So good oxidizers such as chlorine have an effect on bacterial cell walls. That's how they are able to inhibit or kill the bacteria. There is a U of I and a reference down there, which is linked to another reference that I'll be giving you at the end of the presentation. But all these sanitizers can be used. We only talk about the first 4. So if we start with chlorine, and it's probably the one I'm going to spend quite a few minutes on, it is one of the most common elements we have around. Everybody takes sodium chloride probably every day because that is salt. Or everybody drinks water that has been treated with chlorine as a sanitizer. If you start the spout going in the morning, some of us who are sensitive to smell can smell the chlorine, and actually what I do is put water in a container and let it sit, because chlorine is very volatile and escapes easily into the atmosphere. It doesn't do us any harm, but I don't like it personally, but we take it every day. I just wanted to impress on you that it is around us. And so it's a sanitizer as well as a disinfectant. We just define those two terms, and it's both. And you do have liquid sodium hypochlorite in your homes. Probably everybody has that because you have what we call bleach. Bleach has sodium hypochlorite, and it is at a concentration of 5.25% in the household forms that we buy. What does 5.25% mean? It just means 5.25 grams of sodium hypochlorite in 100 grams of water. 100 grams equal to 100 ml. 1 gram equals to 1 ml. So that's basically what that means. And as we shall see in a minute, pH as well as temperature affect the availability of chlorine to do the job we want it to do, that is to kill bacteria. And after using this water, EPA wants to say that in the effluent we do not have more than 4 milligrams per liter. Actually, let me take that back. Organic producers had this issue with too much of chlorine in sanitizing water, but now it's acceptable to have a little more than 4 milligrams per liter in the effluent that is coming out of the tank where we are washing produce. There will be a little bit of chemistry here to be discussed. it's simple. I hope I've kept it simple. You can either follow the chemical reactions here as they are shown, or you can follow the story on the right hand side if you don't want to follow the chemical reactions here. But when you add the bleach to water, the bleach has sodium hypochlorite, which now combines with water to produce sodium hydroxide. That's the one written as NaOH. And then you get the free chloride, which we call the hypochlorite, the HOCl. The HOCl, the hypochlorite, is the oxidizer, and that's the one we call the free chlorine. And we would like it to stay as HOCl, the hypochlorite ion, as opposed to it dissociating to hydrogen ions and the OCl. If it dissociates like that, then we start getting acidification taking place, because the H+, which is a free hydrogen ion, starts combining with oxygen to produce water, as you can see down there, and then you have the chlorine now free as a gas, and it escapes, and that escapes under acidic conditions. So we want to maintain the water system in such a way that we have the hypochlorite, the HOCl ion, present, because that's what causes the oxidation process that kills the bacteria. It is shown better in this slide. Again, you may want to follow the table or the figure. They say the same thing. If I start with the table, the vertical axis there shows how much HOCl we have, or the other dissociation product, which is OCl, the chlorite or the hypochlorite. So it can be up to 100%. On the other hand, at the bottom axis, they're showing pH, from pH 0 to 10. And you know very well that when you tend towards 0, you have a very acidic solution. If the solution is tending towards 10, then you have a very alkaline or basic solution. When the pH is very low, as in the acidic side, 1, 2, 3, you have very low levels of the hypochlorite ion. And then when you get to pH 3, you have it at max, which is almost 85%. And then you get to pH 6, it starts falling again. So you don't want too much of basicity or too much of acidity. But the recommended level is 6 to 7, because at 6 to 7 you don't have too much of acid. If you remember from the previous slide, if you start going towards 4 or 5, you have too much of the H+, the hydrogen ion in there, and it will start combining with the chlorine to form hydrochloric acid, which then causes too much of the chlorine gas to escape. So you don't want to get to that level. If you look at the table, if you have pH 3, which is very basic, you have 99% hypochlorite. You have the acid, and if you have that acid, you don't want that, because the Cl, the gas, will escape. You want your pH about 6 to 7. At that optimal stage, you do have the most stable hypochlorite molecule or something. Then you note that as soon as you start losing the hypochlorite ion at pH 6 to 7, if it starts going down, the OCl, or the chlorite ion, starts going up again. So you don't want that. You want to stay within 6 to 7. And therefore, it's imperative that you keep monitoring the pH of the solution, so that you are maintaining the proper level or concentration of chlorine in that solution. Besides, if you have too much of HCl, if you have too much of the hydrochloric acid, let me go back to this slide. If you have too much of the hydrochloric acid, it's corrosive, and so the container also could react with the acid. Then also when you have too much of chlorine that is being given off in the air, it may be irritating to the workers. And so chlorine is a great antimicrobial and sanitizing agent, and you need to check it regularly, and you need to allow the food items or the commodities that you're washing to have contact with chlorine for 1 to 2 minutes for that to be effective, for the bacterial destruction to be effective. And for different commodities, you have different recommended levels of chlorine. You see, like the root crops, they require only 25 to 50 parts per million of chlorine, whereas the above ground commodities like pumpkins and lettuce, you need 100 to 150 parts per million. The good thing with chlorine, again, is that it is user simple. We talk of user friendly, I guess I would call it user simple, because that wide range there gives you free way to kind of play around with the concentration. For instance, if I want to do 100 parts per million in, I can go with 1.5 teaspoons or 5.25 sodium hypochlorite in 100 ml of water. Or in other words, if I want 100 parts per million in 5 gallons of water, I just need 2 tablespoons, and I have slightly over 100 parts per million. So it's easy to recommend to producers and those who are washing produce that they can just use it. Simple measurements like those should be sufficient in the wash water. I talked about monitoring the concentration of chlorine, because the concentration of chlorine is what is doing the job for you. If you don't have enough, you might as well not be having it, because that's what caused the Colorado cantaloupe farm trouble in the first place. They didn't have any sanitizer in water. But here in Chicago, the Cook County Soil and Water Conservation District sells water analysis kits, and I call them water analysis because you can do different types of tests, bacteria, pesticides, and lead and nitrates. You see them all listed there with the top right hand type of kit, which only costs you $35 to do about 19 or 20 tests. On the other hand, you can go with chlorine strips. If you just want to check on the concentration of chlorine alone, you can use these strips, which 50 of them cost $20, and you just dip them, and they are color coded, so the change in color on those test strips tell you what's the level of concentration of chlorine in water. So from your local offices of public health, soil and water conservation district, as well as extension offices. If extension offices don't have them, but they can tell you where to get these things, you should be able to get the test kits for either the entire analysis or just for chlorine alone.
If you have some questions, type them in there, and we'll try and work them into the presentation. So just want to remind that. Go ahead, James.
Okay. So that's it about chlorine, but the other sanitizer that I want to talk about is the less well-known but very good sanitizer, which is chlorine dioxide, ClO2. It does not react with water like chlorine, and it is easier to retain in water as opposed to chlorine. That means it doesn't evaporate, so it's not a vapor, it's not air. However, it is not as stable as chlorine is, and it cannot be produced off-site. So you have to develop it on-site for best results and for best stability, as opposed to getting it from far. And then there are no simple techniques of monitoring its concentration. So maybe it's a bit more relevant to the larger farms. The larger farms probably can invest a few more dollars than smaller farms for the monitoring of the concentration. And it acts much better than chlorine. As you see there, it's 2.5 times more active compared to chlorine. And then the other good thing about it is that its pH and temperature neutral. It is not affected by either pH or temperature. Neither is it affected by organic matter. And that's one thing I should probably have said. I didn't say that chlorine heads, or I probably did, when I said that you need to clean your containers thoroughly well. Chlorine gets bound easily to organic matter as well as soil, debris and all that. Not so with chlorine dioxide. And it can be used, as you see there, 5 parts per million. That's way less than chlorine, which we said it needs to be about 25 to 200. And the only other thing about it is that it's an irritant. It's not good for the workers. And if you are using it indoors, proper ventilation is crucial. Indeed, less than only 2 parts per million are tolerated in the air. Should be no more than 2 parts per million. We'll say more about that, but the other thing I'll talk about now is ozone. We've all heard about ozone. Ozone is what accumulates way up there. But ozone is a gas that is formed when oxygen, which you know as O2, combines with a singlet oxygen, so O1. And how does this happen in nature? UV light, which are strong rays, as well as lightning, can break an O2, which is the oxygen we breathe. And when that happens, you get all these singlet oxygens that don't have a mate. And you will get some of them getting to combine with other singlets to form the the O2, the oxygen that we know of. But some of the singlets will actually bind with an O2 to form an O3, which is the ozone. And that figure there shows a kind of a cartoon that you would expect to see with ozone. Ozone is very reactive. In fact, you want to call this a radical. Some of the radicals that happen to occur in our bodies, in the cells, are very damaging. In fact, the agents are thought of to be a variety of radicals, peroxide, ozone, various types of oxides. So this is another oxidizer, and it is used quite a bit to purify water in Europe, in Los Angeles, in Milwaukee. In fact, those places boast of having the best water. Indeed, I always wondered why I never smelled chlorine in bottled water. It's because they use ozone quite a bit. And then in the more affluent swimming pools now, they use ozone to clarify water, to sanitize water. People have heard of people saying that they don't like chlorine on their skin, so ozone is being used instead. Now, ozone acts 1,000 times faster than chlorine. It's highly effective, very, very effective. So ozone is increasing in popularity with those people that would like to change from chlorine, and it is very highly effective in destroying bacteria and viruses. Compared to chlorine, it is pH neutral, and it really has no irritation to workers, although there is an exposure limit that I don't have here, which is recommended to workers. And the only thing about it is that you cannot buy it. You have to buy the machine that is an injector. It's an injector. This one that I'm showing there is a generator of ozone, which continuously pumps the ozone into your water, and it acts on the bacteria, and if there are any viruses or any other microorganisms, that will kill this. And the generators can cost from some hundreds to thousands, can be even tens of thousands, 10, 12, 20,000. But according to Trevor Saslow, who is a post-harvest handling specialist in the United States, a couple of thousands will do well for the small farm. So that's the one shown there. The other sanitizer is called peroxyacetic acid, or it's also called paracetic acid, PAA. It's simply a mixture of acetic acid, which we all take anyway in vinegar. It's a mixture of acetic acid as well as hydrogen peroxide, which is another oxide. So that mixture is a very good disinfectant at 80 parts per million concentration in water. Indeed, it is been shown to be very effective on any contaminants, bacterial, microbial contaminants, on melon and cantaloupes. We are thinking here of E-Coli and Salmonella. And you see it's much shorter time of contact compared to chlorine, about 45 seconds. Like all other sanitizers, it has its advantages and disadvantages, and it's unaffected by organic matter.
James?
Yes?
Can you catch this question here? It has to do with the wash water. If you start out with the wash water that is 8.3, so it's got a really high pH, is there anything special about that you need to consider versus if you had a really low pH to start with?
The municipal water is 8.3, so is there anything I should be aware of regarding its use for sanitizing? Yes. We just said as soon as you go over 7, pH 7, then you're starting to lose the capability of the chlorine to be reactive. We want it reactive. We want it to have the capability to oxidize the bacterial cells. So yes, you would probably need to add a weak acid, like acetic acid, especially when it is organically sourced. Acetic acid is recommended so that you bring down the pH towards acidity, so that you now get 6 to 7 or around that area.
Thank you.
Yes, thank you. So PAA has advantages and disadvantages and has low reactivity with organic matter. And I keep talking about organic matter and soil debris because you bring in some pumpkins to wash or melons that are on the ground. They do have debris on them, they have soil on them. So that's why I keep talking about debris. If you put those straight into sanitizing water before you wash them with just water that has no sanitizer, then whatever you are using as a sanitizer will be bound to the debris, the soil. And then it is pH neutral, and because its byproducts are completely safe and mixable with water, acetic acid and water are the byproducts of its the breakdown of paracetic acid, then you have no worries about any residue on the washed product. It's a little bit pricier than chlorine. It's a little bit more expensive, and that's the main thing that probably is a drawback with it. But otherwise, it's a very good sanitizer too. I got another 8 minutes. We started a little bit late, but I got a few minutes to go yet. And I'll use this as my summary slide of the 4 different sanitizers we just talked about. I'm showing them here as they are affected by both pH and organic matter. So there are those that are very sensitive, and the hypochlorite, chlorine, and those that are just sensitive like chlorine dioxide, and those that are not sensitive at all to organic matter. The pH varies peroxyacetic acid, I should have said, look at the range there, 1 to 8. It is pH neutral. I said that, but now you have the figures here. And the first 4 are oxidizers. We talked about that. And I have just added irradiation, which is caused by UV light. Now, UV light can be used to kill microbes on the surface of fruit. And it can also be used to kill any bacterial spores or cells in water. There are 2 issues with that that I've had. Irradiation, does it have any adverse effects on the quality of the produce? Research in Purdue and in U of I here is set to tell us whether there are any issues with the produce being affected by irradiation. But then the issue with disrupting or killing bacterial cells in water, it's not that easy with the UV light, because water tends to become turbid with time. It becomes dirty, and UV light does not penetrate water very well if it's not very clear. So it has those disadvantages. And then radiation is not something that people want to handle just carelessly, so again it's a hazard, potential hazard. And I thought then I would throw also this slide in there about the procedural steps for cleaning fruits and vegetables. And I have said there that you need to keep the water, the wash water, about 10 degrees Fahrenheit cooler than the produce. The reason being that when you have produce coming from outside, you put it in hot water, or if the temperature difference is over 10 degrees, you have what is called suction pressure or osmotic pressure that will draw in water into the produce. Now you don't want that, because the same water may be harboring some bacteria, and you want to ensure that your water is slightly cooler than the produce. How do you don't have to be measuring with, you don't have to be working with thermometers as such, but you can always check or tell what the ambient temperature was when you harvested the apples. And maybe you harvested them very early in the morning, so you are kind of all right, but at midday it's a bit warmer. On the other hand, your water is probably in a sheltered area, so it's probably not as warm as the ambient temperature where the apples came from the orchard. But when you come in with your produce, it's recommended that you first of all do a pre-wash before you do the sanitizing, like I just said a few slides ago. And then you wash with the sanitizing water that has sanitizing agent, and after cleaning with the sanitized water, do another post-wash with clean water. We're talking about potable water, drinkable water that is clean and pure. Okay. Having said that, though, when you harvest strawberries and you want to store them for a few days, or you want to store them because you want to sell in 2 days' time, what do? You don't wash them, because they will become mushy. I don't think they'll become very nice. They will not look very nice in a few hours. So those, the consumer has to wash themselves. What about cantaloupes? If you looked at the surface of a cantaloupe, it would look just like the Grand Canyon. There are caves. I mean, the contour over there is no different than the surface of the moon. Craters and caves and holes and valleys. You have very many nooks and cracks and crannies where the bacteria can hide. So is this washable easily? Not with just water as is, because if you see the blue, if you look at the blue cartoon over there, water has what we call surface tension, and water molecules cohere. They get bound to each other so strongly that spreading of water is not easy. And that's why vessels float on water, because there is surface tension. You have that resistance for anything else to push the water. But when you apply, or when you add soap to water, then you break the surface tension. And that's why our clothes will not be as clean if you wash in water that doesn't have soap. You need to break the surface tension. Similarly, for the chlorine or the sanitizer to get into these nooks and cracks, you need to have a spreader or a surfactant. And indeed, soap has been recommended. 3 ml, which is about like half a teaspoon of soap, household soap, in 1 gallon of water, will spread that out. And I have said there that H.O Feng, he's a professor at U of I, University of Illinois, is doing studies which just look at different surfactants. The same thing with the sprouts. It's been shown that if you don't clean up your sprouts before you cook them or germinate them, actually before you germinate them, then they tend to stay with the bacteria. And I don't know if everybody has been following the news, the food safety news, but so many sprouts have been the cause of foodborne illnesses in fast food restaurants. So that I just wanted to bring that up, because wash water is not always effective if you don't do certain things. I got a couple of references over there. If you don't read anything else, or if you don't go anywhere else, please Google Trevor Saslow. Trevor Saslow. He is in the middle of that slide there. He is the specialist, post-harvest handling specialist, I would say, in the nation. He's probably one of a few. But he has a lot of publications about sanitizing water and how water should be treated. I've also given a few references there. When you go on the internet to look for references and resources, ensure that you have the edu suffix to whatever you're finding, because university-related information is always unbiased. And also, I talked about good agricultural practices. This is the book we use. It's not the only one we use. The Food Safety Begins on the Farm. It's not the only one we use. There are many others out there. They all are about the same, and they are good. And the reference at the bottom there is what has been linked to by the University of Illinois for recommended sanitizers. But
James, there's a question there. Can you handle that question, James?
Okay, I'll answer this. Trevor Saslow is the person you want to Google out for any information regarding wash water. All right. Question by Kathy. Are there any agencies producing a flyer for the general public on how to handle, store, and properly prepare produce? Not that I'm aware of, but as we speak, the Produce Safety Alliance, which is a body or it's a committee that is looking into good agricultural practices, is probably going to address that. So I don't know of one, and I don't know if any of my colleagues on air that are listening are aware of any. I don't have one. Maybe that's something that we need to look into, Kaya. That's something we ought to look at. Well, yeah. Okay. If you're looking, I see the answer. One of the answers here by Chris, that there are some that discuss handling and storage, like wholesale success. Yes, I'm aware of that. But one that is comprehensive, as Kathy asked, we don't have one, and I think we ought to have one. And thank you. Thank you, Chris, for answering that. Yes. Well, also, yes, Chris is also saying there's so much information that you can't just have it in a flyer. And indeed, I wasn't even thinking of a flyer. I'm thinking of a pamphlet, maybe 4, 5, or 6 pages, because there's just too much information. I mean, I had to scale down to what I've just presented just because there's so much information out there. But it gets you thinking about sanitizing water. And I'll keep taking this slide. Any other questions?
Yeah, any questions you can put in the chat there, and we're kind of, I think we're at the end of Dr. Theory's formal presentation here, but the way these work is we're going to stay online and answer questions, so if anybody has to leave, certainly we're not going to keep you from doing that, so if you need to leave the session, go ahead, but anyone that has questions, just type it in the chat, and we'll go through theirs. There's a question on chlorine strips for you, James.
Yeah, thank you. Janet is asking if the chlorine test strips. It's possible. Indeed, I think these test strips are also used for swimming pool analysis. You know, the chlorine concentration analysis. So maybe you can get them there too. Yes, I think so. And Ellen, if Ellen is online, she is the one that actually told me about Soil and Water Conservation District in Cook County. Pam is asking about the P. The P is what? Parasitic? PA? I can't see the whole question.
Can you say a little more about PAA? I'm not familiar with this type of disinfectant. Specifically, I'm wondering about how it affects fish and or if you could easily remove it from water as you can aerate to remove chlorine.
Okay. From what I know, it's environmentally friendly, one of the most environmentally friendly sanitizers, and I expect it to not have any effect on fish. And how can you remove it from water? I guess the byproducts being acetic acid, which is weak, very weak acetic acid, and water, makes it really, really environmentally friendly. It's probably the one of the 5 or so sanitizers that I read about that's probably the best when it comes to ecological considerations. So that's probably that's the best I know. Pam, I didn't attend to your question as well as I should have, but back to the slide on PAA advantages. It has such, the best I can say is that it's acetic acid and water byproducts are such well, the acetic acid is in such low concentration, it has no effect at all on wildlife.
Okay, any other questions?
Hold on.
Questions for James?
Hold on. Biosafe Systems makes one that I have used. Oxidate. Don't know about fish. Okay. I've used Oxidate for different reasons, and it is a very good oxidizer too. At the macro level, I mean the macro organisms, I did not see any precautions, but for microorganisms, it's very effective from that point of view. And I'll check about it.
If everyone can see that link that Deborah sent.
Thank you everyone for participating, and Pam, thank you for the question.
Okay, if there's not any more questions for James, so thank you everybody for attending today.